Hi guys, I know I have been making this video after a very long time, and the reason is I am finding it very difficult to strike a balance between research, the teaching and my fitness, right? So these three things are most important to me, and it's really becoming difficult for me to find the right balance amongst all three. I can manage two very easily, but then the third gets compromised, right? So like in the past few weeks I was focusing more on research and my fitness, and my YouTube channel was getting compromised. I could not make videos daily, and if I focus on fitness and YouTube, then my research gets compromised, so you understand. So I'm trying to figure out I'm trying to find a good balance between all three, so that none of them gets compromised, and it may take a little while for me to get into that mode or that schedule. Now, what since I've been making this video after a very long time, I need a small suggestion from you. Whatever your suggestion is, you can comment down below. And the thing is that in this whole while, I've realized that I've been making videos in a very haphazard manner, right? There's no organization. I'm just making videos on random topics, whichever I feel like is important for your competitive exams. So there's no structured course that I have been following, though I've been making playlists from which you can actually go through a bit of a structure in the coursework. But what I plan now is, for example, if I take a topic, let's say NMR, I plan to finish NMR from beginning to the end, from the very basic level to the advanced level, and then all my videos will be based on NMR. And then for the competitive exam basis, what I can do is make a summary of all those 7 or 8 lectures, particularly from the point of view of competitive exams. So for those of you who are looking for academic help, like in your exams, in your university exams, they can actually go through all of those 7-8 lectures, whatever, however long the lecture series is regarding a particular topic. And those who are looking for competitive exams, they could just go through the summary of those lectures. So if you think this idea is going to be beneficial to you, I would highly appreciate if you could just comment down and let me know whether this works for you or not, right? So it's upon your feedback that how I'm going to proceed with my videos, right? Okay. Now today I'm going to talk about a very important topic, that is fluxional behavior. And this topic, I've seen many students struggle with this topic, and it is somehow very easy. Now there won't be questions directly on the fluxional behavior. Generally in your exams, in your competitive exams, questions will be asked derived on the application of fluxional behavior, and the application is basically in NMR. So to understand fluxional behavior, the NMR is the most important technique by which you can find out whether a molecule is fluxional or not, right? Fluxional basically means rapid exchange of you can say molecules or atoms in a particular complex. So because of that rapid exchange, what happens is the NMR at room temperature is not able to detect that particular change, and it shows that all the 5 atoms or molecules are equivalent, whereas in reality they are not equivalent. Because of the rapid exchange, the NMR is not able to detect the the difference in the environment of all those of all those structures. So but once we lower down the temperature, we can actually differentiate with the help of NMR that both the atoms or both the molecules are in different environment. Okay, I'll talk about you will find out in detail. I'm going to talk about that particular topic, and from now on I'll also tell you the references which I am taking for this particular video. So this particular video I followed 2 books, that is Dynamic Nuclear Magnetic Resonance Spectroscopy, that is by F.A. Cotton, right? And F.A. Cotton is one of the pioneers in the field of organometallic chemistry, and especially fluxional behavior. Like, he has worked a lot on this particular topic, fluxional behavior, F.A. Cotton. And then organometallic chemistry by R.C. Mehrotra. He is an Indian author. This book I have followed. So these 2 books I followed, and there's a few more research papers that I did follow from various reputed journals. One is Chemical Reviews, and then there's Accounts of Chemical Research. So these 2 journals I generally refer to for particular topics, and then these 2 books, right? So now let's just dive into the topic. Okay, right. Okay, so before that, like, it's a ritual now to see whether the video is filming or not. I don't want my time to get wasted, so and I guess who have been following me regularly know this ritual by now. Okay, so like I told you, let's take example of two molecules. One is PF5, right, and then other is FeCO5. So according to the FeCO5 and PF5, so according to the Vesper theory, if you find out the structure for both these molecules, it comes out to be trigonal bipyramidal, right? Trigonal bipyramidal. And what? So I'll draw for PF5. It's the same case with FeCO5. So if you look at the structure, trigonal bipyramidal. So these three fluorines, okay, I'll show them by dotted line. That means they are in the same plane. So this phosphorus and three fluorines are in the same plane, and then there are two fluorines, one above and one below the plane, like that. So this is your trigonal bipyramidal structure. Now if you do NMR of PF5 at room temperature, you can see there are two different kinds of fluorines. Like the fluorines are in two different environments, right? And I'll show it to you with a different marker, different colored marker. Yeah. So if you see these two fluorines are in one environment, right? And then we have this fluorine, the ones in the plane in one environment. So there are two different kinds of fluorine in different environments. So you will see one signal for both these two fluorines, and you will see one signal for these three fluorines. I'm not talking about the splitting pattern right now. I'm just talking about the number of signals you will observe. So you will observe two signals, one for these two fluorines and one for these three fluorines. So there will be two signals observed. That is what theory tells us. But in practical, when we do the NMR practically at room temperature, we only see one signal for this molecule. Now how is that possible, right? That is possible because of the fluxional behavior. Fluxional behavior means these three fluorines and these two fluorines, which are in equatorial and axial positions, they tend to exchange rapidly at room temperature. So the activation energy of this particular molecule of the exchange of fluorines is very, very less. So at room temperature, there is enough energy provided to this molecule that the fluorines can undergo rapid exchange, and these fluorines can go to equatorial and axial positions respectively. Like they could exchange their positions. So because of this rapid exchange, the NMR has certain amount of time to detect. I mean, it takes time to detect the change. So if these fluorines are exchanging very fast or rapidly, the NMR at room temperature will not be able to detect the change, and it will see all these five fluorines as equivalent. So this is basically a fluxional behavior, rapid exchange of these fluorine atoms between in this case equatorial and axial positions. So because of this rapid exchange, the NMR will not be able to detect the different environments of the fluorine, and that's why you are going to observe only one signal. But as you reduce the temperature and you go to say minus temperature, minus 60, minus 70, minus 100 degree, this rapid movement of fluorines slows down, and the NMR is then able to detect the positions of the fluorines. So it can differentiate between the axial fluorines and the equatorial fluorines. And once it is able to distinguish between the two fluorines, so at a lower temperature, at low temperature, you are able to observe two signals. So at lower temperatures, you are able to observe two signals, one for these two fluorines and one for these three fluorines, in the ratio 3:2. Since there are three fluorines here, so 3:2. So at low temperatures you observe two signals, and at high temperatures or at room temperature you only observe one signal. Similarly, if you carry out the 13C NMR, so here you are carrying out the 19F NMR to find out the structure of PF5 at lower temperatures. Similarly, for the case of FeCO5, if you carry out the 13C NMR, again you will see only one signal at room temperature, but as you lower down the temperature, you will observe two signals, similar to the structure. Like it also has trigonal bipyramidal structure, and similar to the case of PF5, at room temperature there is rapid exchange of CO, so the NMR is not able to detect the difference between the different environments of CO, but at lower temperature it is easily able to detect the difference between these two CO groups and these three CO groups. Like there are three CO groups in the plane, and there are two COs below and above the plane, so it is easily able to detect the difference, right? Okay, so this is basically your fluxional behavior. So it was firstly observed in these two molecules, PF5 and FeCO5. Like earliest it was observed in these molecules. Now there is something called Berry pseudorotation, right? I'll write it down. It's called Berry pseudorotation. You might have seen a lot in the exams, right? I'll just write it clearly, Berry, Berry pseudo-rotation. So what is this Berry pseudo-rotation? So Berry was actually the person who said that it's actually known as Berry mechanism, but like we'll see in just a while, that why is it called Berry pseudo-rotation. So the Berry was the scientist who actually said, how this rapid exchange of fluorines is taking place. So he proposed a mechanism on how this PF5, how these fluorines are exchanging positions, like this fluorine and this fluorine, how are they exchanging positions. So he proposed a mechanism for that, and we'll look into the mechanism first. So what was the mechanism, right? Now what I'll do is, let's say, okay, I'll just draw it again, so to explain it in a better fashion. Right, so what he said was, let's say this is F3. I'm assuming this to be F3, right? This is your F1 and this is your F2. So F3, F1 and F2 are in the plane, which I've shown by dotted line. And then we have F4, which is above the plane, and F5, which is below the plane, right? Or you can imagine F4 to be going inside the whiteboard and F5 coming outside the whiteboard. So this is there. Now what he said was, when you provide certain energy, it changes from trigonal bipyramidal to square pyramidal. So this trigonal bipyramidal structure changes to an intermediate structure which is square pyramidal. So if I draw the square pyramidal structure, you can imagine it this way. So, right, I'll use a different marker. Okay, so we have fluorine now over here. Then we can assume this, let's say this F3 goes above the plane. This F3 goes above the plane. Then we have let's say F1, F2, F4 and F5. So this is the kind of geometry it adapts. This is now square pyramidal structure. So this is an intermediate where now F3 is above the plane and F1, F2, F4, F5 come in the plane. So this is the square pyramidal structure, right? Okay. So this is what is happening, right? Now what happens is, then further, this then further converts into F over here. Now your F1, F2 go, then it converts back to the trigonal bipyramidal structure. So this intermediate is higher in energy. Say, let's say this difference is 30 kilojoule per mole. So at room temperature, enough energy is provided for this to convert to this intermediate, right? Now from this intermediate, it can either go back to this structure, which is trigonal bipyramidal, which is lower in energy. So it will like to adapt the lower structure. Or what it can do is, this is one structure it can adapt. The other structure it can adapt or adopt is with F1 and F2 above and below the plane, and now your F4 and F5 come in the plane. So now your F4 and F5 come in the plane, right? Sorry for the haphazard structure. So now your F1, so you can see clearly over here that your F1 and F2 are now, instead of F4 and F5, your F1 and F2 are above and below the plane, and your F4 and F5 are in the plane. Whereas for this structure, F1 and F2 are in the plane and the F4 and F5 fluorines are above and below the plane. So you can see the rapid exchange taking place. At room temperature, it converts into this intermediate. Now this intermediate will like to go into the lower energy state, which is either this or this. So it can go into either of the two energy states. It has an equal probability to go to this energy state or this energy state. So you can see there's a rapid exchange of fluorines taking place. I've taken the example of F1 and F2. It could also be F2 and F3. It could also be F1 and F3. It could be any one of them, right? So this is what Berry gave the mechanism. Now why is it called pseudo-rotation? It is known as pseudo-rotation because if you see this difference between the structures, what is the basic difference? Okay, what is the basic difference between these two structures? Now to explain the basic difference, why is it called pseudo-rotation, I will take one example. Let's say we have this duster, right? This is your duster, and if you take this duster, let's say we'll take this structure. Okay, we'll take this structure. So your F1 and F2 are in the plane, right? So we have, I hope you can see, we have F1 over here, F2 over here, like that. So this is your plane. This duster is your plane. We have F1 over here, F2 over here, and F3 like this over here, right? So this is your F3, this is your F1, this is your F2, and your F4 is over here above the plane, and your F5 is below the plane like this, right? Now what happens is, if I pass an axis like this, if I pass an axis like this through this, passing through F3 and the phosphorus. So we have phosphorus in the center, we have F3 over here, and we have F1 over here, F2 over here, and F4 above the plane, F5 below the plane. Now I pass an axis passing through the fluorine and the fluorine, the F3, and I rotate it by 90 degree. Now if I rotate it by 90 degree and the axis is passing through the phosphorus and the fluorine, if I rotate by 90 degree, there will be no change in the phosphorus and F3. The phosphorus and F3 will remain in the position. But the F1 which was over here, if I rotate by 90 degree, the F1 goes above the plane. The F1 goes above the plane, and let's say we have F4 above the plane. This F4, if I rotate by 90 degree, goes in the plane. So now your F4 is going inside the plane and your F1 is going above the plane. And similarly we had F2 over here, and now F2, if I rotate by 90 degree, goes below the plane. And we had F5 over here, if I rotate by 90 degree, F5 also comes in the plane. So now your F4 and F5 are in the plane, and your F1 and F2 are above and below the plane. And that is what exactly is happening over here. If I rotate this molecule by 90 degree, if I pass axis through this side, if I pass axis through this phosphorus and F3 and rotate by 90 degree, now your F2 and F1 are above and below the plane, whereas your F4 and F5 are now in the plane. So you can see, if I rotate it by 90 degree, I get this structure, and that is why it is called Berry pseudorotation. Like, to simplify the mechanism, it is commonly known as Berry pseudorotation, because it looks like you have rotated the molecule by 90 degree, but that is not actually what is happening. Actually, it first converts into the square pyramidal structure, and then it interconverts into either this or this. But to simplify, they call it pseudorotation because it looks like it is rotated by 90 degree, and that's why the term pseudorotation. It's not actually rotating, it looks like it has been rotated by 90 degree. So that is why it is called the Berry pseudorotation, right? And just let me check whether the video is filming or not. Right. So now what is the application of fluxional behavior? What exactly is the application? So now let's look into the application. So there was a question that was asked in a June 2014 CSI NET paper for 4 marks, and the question was, we have MnCO3. So we have a complex MnCO3 which is attached to eta 3. Eta 3 means hapticity of 3. So there are 3 carbons we have like this, and eta 3 means it's attached to all the 3 carbons, right? So they had asked how many number of signals will we observe for this particular, if you take the NMR, the proton NMR, how many number of signals will be observed for this complex. So if you see over here, we have one hydrogen over here, right? We have one hydrogen over here, we have 2 hydrogens over here. Similarly, we have 2 hydrogens over here. So this was the question that was asked, this was the complex given to us, and they had asked how many number of signals will be there. They had not obviously drawn the structure, they had just given MnCO3, eta 3, C3, H5. They had given like this, eta 3, C3, H5, MnCO3, how many number of proton NMR signals will you observe for this particular complex, and they had given 4 options, right? Now how many number of signals will you observe? Now this is where you need to understand the fluxional behavior, and they had asked particularly at low temperature. They had mentioned at low temperature, I think they had given -70 degrees Celsius, right? So at low temperature there will be no fluxional behavior observed. Okay, at high temperatures fluxional behavior is observed, but at low temperature you do not see fluxional behavior. So if you look at this molecule, now at high temperature I will tell you what will happen at high temperature. Let's say I label this HA, I label this HB, I label this HA, I label this HB, and I label this HC. Now at low temperatures, if you see, at low temperature means there is no fluxional behavior taking place. That means this HA, HB are fixed in its position. So you can say that at low temperatures the molecule is rigid. So this HA and HB are fixed in its position, and this HA and this HB are also fixed in its position. So if you look at this HA in respect to HC, this HA is in syn. It's syn to HC. Okay, this HA hydrogen is syn to HC, whereas this HB hydrogen is anti to HC. So this HB is actually it's anti to HC. So these two are in different environment because now they are rigid. At low temperature, this molecule is rigid. So HA is syn to HC and HB is anti to HC. So they are in different environments. So this proton and this proton are going to give different signals. And this HA and HB are also similarly HA. I have labeled both of them HA because they are in the same environment. This is also syn to HC. This is also syn to HC. Similarly, HB is anti to HC and this H is also anti to HC. So these two HB hydrogens are in same environment, and these two hydrogens are in the same environment, and HC is obviously in a different environment. So if you see the number of signals, so one signal for both these two HAs, one signal for both the two HBs, and one signal for HC. So you will observe three signals in the ratio 2:2:1. You will observe three signals in the ratio 2:2:1, and this was the answer. Three signals in the ratio 2:2:1. How? There are two HB atoms. They will show one signal. There are two hydrogens, so 2:2. There are two HA atoms, so again ratio 2, and there is only one HC. So that is why the ratio 2:2:1. Right? Now what will happen at high temperatures? At high temperatures, this HB and HA can rapidly exchange. This HB and HA can rapidly exchange. So because of this rapid exchange of HB and HA at higher temperatures, there will be no syn and anti with respect to HC, because HA and HB are rapidly exchanging the positions. So the NMR will not be able to distinguish between HB and HA. Because of this, you will only see one signal for both these two hydrogens. And since now all the four hydrogens will become equivalent at high temperatures, because of rapid exchange of HA and HB, this becomes HA, let's say, this also becomes HA, and this also is HA, this is also HA. So now you will see at high temperature 4:1. You will see only two signals in the ratio 4:1. Because all these four hydrogens now become equivalent. Whereas at low temperatures you will see 2:2:1. So this is the application of your fluxional behavior. So they might not directly ask you a question on fluxional behavior, they might give you questions based on the NMR. Alright. So this was one question for 4 marks in your June 2014 CSIR NET paper. Right? Okay. One more important thing that I want to discuss is, this question has not been asked yet, but I am quite sure it will definitely be asked in the future. And the question is, you have this complex copper PC2H5 whole thrice, okay, and then this is attached to eta1 C5H5. How many number of signals at high temperature and low temperature will you observe for this eta1 C5H5? Okay, so I will just tell you, at high temperatures you observe 3 signals, and this is at high temperature, and at low temperature you observe only 1 signal. Now how is that possible? The reason is fluxional behavior in eta1 C5H5. Okay, and how is that fluxional behavior taking place? We'll look into it. So if I just draw the copper complex, copper attached to some complex, and then it's attached to your cyclopentadiennyl complex. This is your eta1 C5H5, right? And we have one hydrogen over here, right? Similarly, we have one hydrogen over here, one hydrogen over here, one over here, one over here. So it's C5H5. Now if you look, I'll denote this copper by metal. That will make it easy. So I'll denote this copper by metal. Okay. Now what happens over here is, how the fluxional behavior takes place. You can just show this metal and carbon bond breaks. Okay. So let's say we are talking about this hydrogen, right? Now at high temperatures it shows 3 signals. Why? Because this hydrogen is in different environment, this hydrogen is in different environment, and this hydrogen is in different environment. So there are 3 kinds of hydrogen: HA, HB, HC. This is also HB only, and this is also HC. So there are 3 different kinds of hydrogens. One is this hydrogen, one is this hydrogen, and one is this hydrogen. That's why at high temperatures you observe 3 signals. But what happens at low temperature? So at low temperature, and before coming on to this, just let me check for the video because this is a very important topic. Okay, so it's already 25 minutes and I have a few more things to tell, so maybe I'll make another video. What happens is, there are 3 different kinds of hydrogens, so you get 3 signals at high temperature. But at low temperature, I told you the opposite. I'm very, very sorry. Excuse my mistake. It is opposite. At low temperatures, you will see 3 signals, and at high temperatures, you see only 1 signal. Sorry, very, very sorry. All right. So because at high temperatures rapid exchange takes place, fluxional behavior is high, so you'll only observe 1 signal, whereas at low temperatures you will see 3 signals. So at low temperatures no fluxional, its molecule is rigid, so there is no fluxional behavior, because of which you will observe 3 signals for 3 different kinds of hydrogens. But what happens at high temperatures? Now at high temperatures fluxional behavior takes place, and what really happens is this metal it breaks over here. Okay, it breaks like this and joins, let's say, over here, and okay, sorry, or you can just show like this. This double bond migrates over here, this double bond migrates like this, and you get a metal attached over here. So if I draw the structure, this is your hydrogen, earlier one. This double bond migrates over here, and now your metal is attached at this position. Similarly, you can show this double bond then migrates like this migrates like this, and then your metal gets attached over here. So one more structure you can draw like this. Now your metal gets attached over here. So you can see you can similarly draw all these structures of this particular flux. So it is rapidly exchanging in these structures, and because of which the hydrogen now it looks like it's equivalent to the NMR, because the NMR cannot detect this fast change of fast exchange of hydrogens, or the fast exchange of the metals, because of which it thinks all the 5 hydrogens are in the same environment and it gives only 1 signal. Whereas at low temperatures, once this fluxionality becomes very slow and the NMR is able to detect the different kinds of environment the hydrogen is in, it shows 3 signals, right? So this is again one application of your fluxional behavior. So because of the eta 1 C5H5, because of eta 1 cyclopentadienyl complex, it is that particular reason, because of the cyclopentadienyl complex eta 1, that it is showing different signals at low temperature and high temperature. So the fluxional behavior is shown by eta 1 C5H5, because of which we observe this kinds of NMR patterns. Now, one important thing that I want to tell you is, and this question might have occurred in your mind, and that is that what is the difference between resonance and fluxional behavior? Once we are drawing the resonance structure of benzene also, we are showing like this 4-5 structures. So what is the difference between resonance and fluxional behavior? Now the difference is that in resonance, all the, let's say whatever number of resonance structures you have drawn for a particular molecule, all those 5 resonating structures are higher in energy than the original molecule, right? So for example, you are drawing the resonance structure of benzene. All the resonating structures of benzene are actually higher in energy than the original molecule. Okay, all the resonating structures of a particular molecule will always be higher in energy than the original molecule. It's just another way to depict the molecule. The original molecule will always be lower in energy than all the 5 or than the resonating structures. How many number of resonating it does not matter how many number of resonating structures are there. The energy of the original molecule will always be lower than your resonating structures. Whereas when you are drawing the fluxional behavior, when you are showing the structures for the fluxional behavior, all the structures are equivalent and are equal in energy. There's no one structure which is higher or lower in energy. All the structures that I draw for fluxional behavior have equal energy, and that is and the original molecule also has that particular energy only. It does not have higher or lower energy. Whereas for resonating structures, the resonating structures will always have higher energy than the original molecule. The original molecule will always be lower in energy, right? So that is the basic difference between your resonance and your fluxional behavior. So these kind of questions are asked in interviews. This was asked to me, and that's why I'm telling you the answer, right? So if you can actually answer that at that particular point of time in the interview, the interviewers will be highly impressed by you, right? So anyway, there are few more topics from fluxional behavior, few more molecules or complexes that I need to discuss, which I might discuss in my next video, right? So I hope you like it, and do give the feedback to the question that I had asked, that whether you would like a structured courseware or not, coursework or not, right? So just let me know that, right? So thank you so much.